Hello friends, myself Sagar, and in today's video I'm going to discuss organic name reactions for JEE and NEET examinations. So I made totally 3 videos, and this is the first part among those 3 videos. So I have taken few reactions in this first part. Let us look the list of reactions. So in today's video I'm going to discuss these 12 reactions with their detailed mechanism. So you can see from 1st to 6th we got the reactions from the first year, and from 7th to 12th we got reactions from the second year as haloalkanes and haloarenes topic. So this is a list of reactions to be discussed today. The first one, we need to start with the first year. So you got this reaction, Kolbe's electrolysis reaction, in class 11th hydrocarbons topic. And Kolbe's electrolysis method, as all of you know, that is a method of preparation of alkanes from sodium salt of carboxylic acids. So when sodium salt of carboxylic acid undergoes electrolysis, it produces an alkane ethane if we start with the sodium acetate. Along with that, we'll get a byproducts like carbon dioxide, hydrogen, and sodium hydroxide. So the detailed mechanism for this reaction will be, in the first step, the sodium salt of carboxylic acid, as you can see, this is a strong electrolyte, dissociates to form acetate ion and sodium ions. Then as electrolysis reaction, both the ions start migrating towards the respective electrodes. The first one, acetate ion, start migrating towards anode, and at anode this oxidation takes place. Is going to be the oxidation is going to lose 2 electrons to form acetate free radical. And once you get acetate free radical, as you can see, acetate free radical is unstable. It can be elimination of carbon dioxide from this to form more stable methyl free radical. Along with that, we'll get carbon dioxide gas evolved from this. So in this step, we'll get generation of a free radical here. So that's methyl free radical. 2 of such methyl free radicals combines or coupling reaction to form ethane. So ethane gas is evolved on anode electrode on which oxidation takes place. The second reaction, or the second species, which is migrating towards cathode, will be the water. And you can see in this one we got water gaining electrons, or even Na plus also can gain electrons, but among these two, H2O can gain electron easily compared to Na plus. That's the reason why H2O gains 1 electron. Reduction takes place to form hydroxide ion and hydrogen free radical. So the reasons for this, because Na plus and H2O, H2O can gain electron easily because of this, can be taken in electrochemistry topic by using SRP values. And by seeing SRP values and over potential concept, we can easily tell that H2O can gain electron easily compared to Na plus. And so you got H hydrogen radical here. So 2 of such radicals combines to form hydrogen gas. So the 2 gases evolved here, the first one is ethane at anode and hydrogen gas at cathode. So the 2 gases evolved, and Na plus, what you got in the medium, combines with OH minus to form the byproduct NaOH. So when it takes sodium acetate upon electrolysis, results in the formation of alkane ethane. Along with that, we'll get these byproducts. Now you can see, if you take any other carboxylic acid, you can prepare easily the hydrocarbons or alkanes, but it's having few limitations, this reaction. Now the first limitation is we cannot prepare methane by using this method. And the reason for that, why we cannot prepare methane, as you can see, the mechanism here is like coupling of 2 free radicals. And if you take coupling of free radicals, you don't get formation of like 1 carbon alkane. So that's the reason why this is the first limitation for Kolbe's electrolysis reaction. The second one is we can prepare only even numbered alkanes by using this method. And the reason again the same for that, because the coupling reactions will get always whatever you take free radical with the even number or odd number, you get always an even number here. So that's the reason why it's only even numbered even numbered alkanes can be prepared by using Kolbe's electrolysis. So this is the first reaction, Kolbe's electrolysis, preparation of alkanes. So the next reaction I'm having is Birch reduction. Birch reduction and reduction using Lindlar's catalyst. So these two reactions will come in only one bit there. It's the preparation of alkenes from alkynes. So both differ in one way if we take like stereochemical way. So in the case of Birch reduction, you get formation of trans-alkene. And in the case of reduction by using Lindlar's catalyst, you'll get formation of cis-alkene. So what makes the difference now? So that we get two different stereochemical products here. Let's start with Birch reduction first. Alkynes on reduction with the sodium liquid ammonia to form transalkenes. So this is a reduction now. So let me take first alkyne, then passing hydrogen gas. In the presence of sodium and liquid ammonia, it results in formation of always transalkene. And why you will get transalkenes can be justified by taking its mechanism. So let me take that. At first I had taken mechanism by taking an alkyne to butene, butene. So in the first step, you can see here it's in the presence of sodium and liquid ammonia. So in the first step, what happens? Butene, triply bonded carbon atoms. So we got 2 pi bonds, 1 sigma here. So sodium is having tendency of giving electrons. So donates 1 electron to the carbon, and simultaneously there's a cleavage of 1 bond here, homolytic cleavage. So 1 electron on this carbon and 1 electron on this carbon. So results in formation of you can see here this carbon is having negative charge and this carbon is having 1 unpaired electron. We can call this as is like combination of like 1 carbon or can take carbanion and free radical. So the name given for this is radical anion. So the first step, we get formation of radical anion, and radical anion, as you know, it's unstable. So the next step, the carbon having negative charge, this carbanion will abstract a proton from ammonia, and as you can see, it is abstracting H plus. The bonding electrons will shift on the nitrogen, and it converts this into NH2 minus. And NH2 minus will combine with the sodium ion, eliminate less sodium amide, sodamide. So after abstraction of proton is converted into the species, or can take like this is a free radical. W1 carbon is having 1 unpaired electron. So the next step will be this free radical gains again 1 electron from the sodium, and as it donates is converted into Na plus. Then this carbon is getting a negative charge, the lower pair of electrons, so it's converting into a carbanion, or as you can see W1 carbon is having negative charge, so said to be a vinyl carbanion. And this vinyl carbanion will again abstract a proton from ammonia, and again the same procedure as you have done in the second step here. So we get formation of this is eliminated as NH2 minus, and we get formation of alkene, and stereochemical way if we take, we get always formation of transalkenes in this way. And the reason exactly for that why it is only the trans can be taken from this step. As you can see in this step, we got W1 carbon is a negative charge, and if we take the stability of this one, is more stable only when the methyls, the 2 methyls on the W1 carbon atoms are far away, and it orients in such a way that they should be far away. And if we take the orientation far away, it has to be always the transalkene. So the main stereochemical or stereochemist of this reaction decided by the last step from vinyl carbanion to alkene. So this is regarding Birch reduction, in which we convert alkynes into transalkene by using sodium in liquid ammonia. So after this, we have one more similar reaction, the preparation of alkenes again from alkynes, but only one change here. So in the place again the same hydrogen gas will need to pass, but in the presence of not like sodium and liquid ammonia, so you got palladized charcoal or palladium carbon. Okay, this is a very simple reaction, conversion of alkyne on like partial reduction, conversion of alkynes into cis alkenes. If we see the mechanism for this one, as you can see, you got palladized charcoal solid surface, so it means there has to be a adsorption, and alkynes, the alkyne molecules are having more extent of adsorption compared to alkanes, so it's the best way to convert like alkynes to alkenes. And the reason for why the stereochemistry is cis alkene here, while get only cis alkene by this reaction, it can be explained by taking, okay, so all of you know regarding adsorption, and if you take this as catalyst surface, the hydrogen molecule will be adsorbed on that, and the same actually alkyl molecule also adsorbed. And if you take addition of hydrogen molecule across this bond, pi bond or triple bond, so it has to be from only one side, because of okay, it is oddly adsorbed on the surface, so it should be added to the from only one side, and results in formation of only cis alkene. So the mechanism is like only the adsorption we're having in this one. That's the reason why we'll get formation of cis alkenes. Okay, this is reduction by using Lindlar's catalyst, and the Lindlar's catalyst we can take it as palladium carbon, or can take palladized charcoal. It's deactivated with the poisons like quinoline, so that we take it as a Lindlar's catalyst. And in the case of if you use Lindlar's catalyst, you'll get always formation of cis alkenes. Okay, this is regarding preparation of alkenes by using two methods. One is Birch reduction, and second one is by using Lindlar's catalyst. Okay, this is preparation of alkenes. Next reaction we got is Friedel-Crafts alkylation. Okay, here also we got two similar reactions. The first one is Friedel-Crafts alkylation, and the second we got is Friedel-Crafts acylation reaction. And these two reactions also look like the same. Only one change here, as you can see, alkylation. We need to introduce alkyl group in aromatic system, like I got is benzene here. So if you introduce alkyl group, I have taken as generally here R. So one of the hydrogen of this benzene ring replaced by alkyl. And to replace this, we can use any reagent, like for example, it can be alkyl halide, or it can be alkene, or it can be alkyne, or it can be alcohol in the presence of Lewis acid. Okay, now which is the intermediate involved in this reaction? Let me take that. So at first, what we take in the Friedel-Crafts alkylation, we start the benzene aromatic compound. On reaction with alkyl halide, I got alkyl halide here. It can be anyone, alkene, alkyne, or alcohol. In the presence of Lewis catalyst, anhydrous aluminum chloride results in formation of alkyl arene. Right, now this reaction involves carbocation as the intermediate, and carbocation intermediate is obtained by any one of these reagents. So I take a mechanism by taking alkyl halide as a reagent in the presence of anhydrous aluminum chloride. Right, you can see here mechanism for this one. At first, alkyl halide molecule RCl reaction with the aluminum chloride AlCl3, and all of you know that aluminum chloride, aluminum is having like electron deficient, so it can act as a Lewis acid here. Okay, the chlorine, which is having lone pair of electrons, donates electron pair to the aluminum to form a species like look like the chloronium ion, in which chlorine is having positive charge and aluminum is having negative charge here, and highly unstable because of the charge present, dissociates to form the main component. What you want for this reaction is carbocation. So we'll get generation of carbocation like this, and along with that we get counter ion AlCl4 minus. Now in the next step, this carbocation will get abstracted from the benzene ring. As you can see, the pi electron density we're having on this. So the abstraction of carbocation from the benzene ring results in formation of, you can see this species ring membered, and one of the pi bond is broken here, and one carbon is having positive charge. So this we can take it as arenium ion. So we get formation of arenium ion in the next step here. So this arenium ion is more stable because of, we can write resonance structures for this, and because of resonance more stable, so the next step will be aromatization. As you know, this is one carbon is having positive charge, and AlCl4 minus will abstract a proton, and the bonding electrons between the carbon hydrogen now will shift here between those two carbons. As a result, we get formation of double bond there, or can take an aromatic compound. So in this way we convert benzene, or we can insert alkyl group in aromatic system. So this reaction is called as Friedel-Crafts alkylation reaction, and the intermediate involved here is a carbocation. You can take many reactions. So you got reaction like by giving benzene upon reaction with the methyl chloride in presence of anhydrous aluminum chloride results in formation of, in the place of R we need to write a methyl CH3. That's will get formation of toluene or methyl benzene. So this is a mechanism for Friedel-Crafts alkylation reaction, and as said here, many reagents are there, many ways to get carbocation. So I taken only alkyl chloride here. It can be alkene you can take to get carbocation, or it can be alkyne, or it can be alcohol. Right, that's regarding Friedel-Crafts alkylation. The next reaction we got is Friedel-Crafts acylation reaction. And if we take acylation reaction, I said only one difference now. In the place of alkyl, we need to take the group here as acyl. So I taken one example here. We need to introduce a group here, acyl, into an aromatic system, and the reagents for that, you can use any one out of the two reagents here. It can be acyl halide, or you can take even anhydride. So I take a mechanism here by taking acyl halide formula RCOCl. In the presence of, as usual, it's a Friedel-Crafts reaction we are taking, right? So in presence of Friedel-Crafts catalyst, anhydrous aluminum chloride. Okay, it's a conversion of benzene into, as you can see, this compound. We introduced a group here, COR or RCO. So the reaction is called acylation, and we'll get the classes of compounds belongs to the ketones. As you can see, C double bond O, and you got two fragments attached to that. Right, the mechanism for this reaction will be at first similar exactly. You got previous reaction like by taking RCl. In that place you got RCOCl, and again the first one is complexation there. It forms a complex in which chlorine is having positive charge, and it's a highly unstable one. Breaks to form, okay, the main component what you want in this reaction is a cation, right? Acylium ion. And you can take this acylium ion, you can take it as unstable because of in this we got oxygen, which is more like negative atom is having positive charge. It changes to for the more stable form like this, in which carbon is having positive charge. Once you get this species formed, or you can take a cation or acylium ion, and so like carbocation is also exactly the same step here. Okay, this acylium ion is abstracted by the benzene ring. Okay, take this reaction as like electrolytic substitution reaction. One of the hydrogen should be replaced by the group here. Okay, electrolytic substitution reaction. So you get formation of again the same like arenium ion here, and once you get arenium ion is resonance stabilized. So it is okay, resonance stabilized. After that, so it should be more stable one, right? So having positive charge, and to remove this positive charge, the next step will be abstraction of proton from a base. You can see here AlCl4 minus will abstract a proton, and bonding electrons will shift between the two carbons. As a result, it forms aromatic compound here. So this step is called aromatization, with elimination of HCl, and there is a regeneration of aluminum chloride. So in this way, we can take Friedel-Crafts acylation reactions, conversion of or can take introducing acyl group into an aromatic system, and the reagents for this we can use acyl halide or can use anhydride. Okay, that's regarding Friedel-Crafts acylation reaction. So the next reaction we got is okay, Wurtz reaction. We got three reactions similar here: Wurtz reaction, Wurtz-Fittig reaction, and the third one is Fittig reaction. Okay, so let me start with the first one here, Wurtz reaction. So in this reaction, this is actually reactions of alkyl halide, or can take even like preparation of alkanes from the alkyl halides. Right, now if we take a reaction of alkyl halide with the sodium, let me take here. So I got 2 moles of alkyl halide, methyl bromide. The reaction with the sodium, in the presence of solvent here, dry ether, which is having its role, the importance, dry ether to form ethane. Okay, this is a method of conversion of alkyl halide, like I take first reaction as methyl bromide into ethane. And you can see in this one, right, this is if we relate actually number of carbon atoms in alkyl halide and ethane, you can see it's like 1:2 ratio, or if we take alkyl halide with 1 carbon, we'll get alkane with the 2 carbons. So it means the alkane obtained in Wurtz reaction will be having double the number of carbon atoms compared to in alkyl halide. Right, so that's a reaction called Wurtz reaction. And the second one more reaction I have taken here by taking ethyl bromide. Okay, again 2 moles of ethyl bromide, reaction sodium metal in presence of dry ether results in formation of N-butane. Right, so this is 2 examples, and the reaction is called Wurtz reaction here. Now let me take the reaction mechanism, how it takes place through the formation of water intermediate. In the first step, as you can see here, we got the sodium metal and alkyl halide. Alkyl halide reacts with metal first. It can be taken as sodium. I take generally M here. It can be taken for any organometallic compound. So in this M, we can take it as sodium. And this metal, you already know that you got in you got in the previous reaction by using sodium and liquid ammonia. Sodium can easily donate one electron, exactly the same way here also it donates one electron, and this bond between carbon and halogen is broken in homolytic fashion, results in formation of with one unpaired electron. We call this as like free radical, and along with free radical you get formation of salt M plus X minus. Right, so in the first step you got formation of free radical. The next step will be this free radical, what you got in first step, reacts with again one more mole of sodium, again take metal, again the same one, so metal will donate one electron to this free radical, and as a result it converts this carbon free radical into carbanion, and along with that, as it lost electron, so converted into cation. So we'll get like again a salt form here, R minus and M plus. So you got okay, you generated carbanion here, right, R minus. The last step will be attack of this carbanion on alkyl halide molecule. You can see the carbanion R minus will act as a nucleophile, will attack on the carbon, and as a result the bond is broken in a heterolytic fashion. X is eliminated as X minus, and this X minus combines with M plus, eliminated as a salt. Then you got main compound here, as you can see R minus attacking on alkyl halide, so you get formation of RR, and you can see in this one it started with RH, we end with RR. That means number of carbon atoms in the product or the obtained alkane is double the number of carbon atoms in the alkyl halide. Okay, and you can see one more, can stress on this. So we got the step involved actually. Okay, the last one is it's like SN2 reaction or SN2 attack of this carbanion that act as nucleophile to the alkyl halide molecule. Right, this reaction is called Wurtz reaction, conversion of alkyl halide into alkanes. Right, just regarding the Wurtz reaction. Next reaction we got, okay, let me take one more example for this one. And this reaction we got in one of the JW paper also. So this is conversion of 1-bromo 3-chloro cyclobutane into the compound obtained actually, okay, is bicyclobutane. As you already know that the cyclic compounds difficult to prepare, right? So this method is the best way to get this compound bicyclobutane, and you can see okay why it is best, because you're getting 95% yield here by some Wurtz reaction. Right, the simple reaction it is 1-bromo 3-chloro cyclobutane, the compound upon treatment with sodium metal. Wurtz reaction takes place with the elimination of two compounds, two organic compounds, NaCl and NABr, to form bicyclobutane. Right, so this is regarding Wurtz reaction, and it also got some limitations. The limitations for this reaction are, as you can see the previous one, you got ethane. If you use methyl bromide, if you take ethyl bromide, you're getting a butane which contains even number of carbon atoms. So the first limitation will be we can prepare only the symmetrical alkanes by this method. We can prepare even unsymmetrical also, like for example alkanes having odd number of carbon atoms, but the main problem is to get that we should take like two dissimilar alkyl halides are taken as reactants, and if you take in this way it always results in the formation of mixture of alkanes, not only one product. And if you get mixture of products, it will be difficult to separate those actually. That's the reason why. So the preferred one will be for the Wurtz reaction, so we take with only one alkyl halide. Let me take one example. If you take like a mixture of methyl bromide and ethyl bromide, so the number of compounds obtained in this one will be, 2 moles of methyl bromide combines to form ethane, and 2 moles of ethyl bromide combines to form N-butane. It can be even the combination, like 1 mole of methyl bromide, 1 mole of ethyl bromide, and it forms odd numbered alkane, that's propane. But as I said, the problem will be the separation here, so we get mixture of all these three alkanes. So this can be listed in the limitations for the Wurtz reaction. The next next limitation we got is we cannot prepare methane by using this method. As you can see, the reason for this also, there's a coupling again reaction here. There's a coupling reaction, and if a coupling reaction, so methane cannot be prepared by using this method. Right. The third limitation will be, in the case of tertiary halides, we cannot apply the Wurtz reaction. Like for example, in the place of like methyl bromide, if you want to use tertiary butyl bromide, there's no reaction possible, and the reason can be taken by using this mechanism. Now the reason can be, as you can see, it's forming, the last step is very important there, SN2 attack here. If we're having a tertiary butyl carbanion, and tertiary butyl carbanion cannot act as like a nucleophile. Of course, it's more basic in nature, but it cannot act as a nucleophile because of the steric hindrance. So there's no formation of alkane takes place if we take any tertiary alkyl halide. So that's the reason why we cannot take tertiary halides in this one. And the last one, in this method we cannot prepare alkane containing outnumbered carbon. Right, that's also we discussed that point already. So that's limitations of Wurtz reaction. And exactly the same way, we got two more reactions here. Wurtz-Fittig reaction. All right, so in this case, Wurtz reaction, we got 2 moles of alkyl halide. In Wurtz-Fittig reaction, we take 1 mole of alkyl halide and 1 mole of aryl halide. And again, actually both heating, or again treatment with sodium metal in solvent and dry ether. Right, now if we take aryl halide and 1 mole of alkyl halide, treatment with sodium metal in presence of dry ether, results in formation of alkyl arenes. Take an example, if you take like starting with chlorobenzene and chloromethane, treatment with sodium metal in presence of dry ether, it will form, so just change here in place of carbonate, right, methyl CH3. Right, so let me take mechanism for this reaction now, exactly the same like you got in the previous reaction. So at first, sodium will give 1 electron here, and the bond between carbon and halogen is broken in homolytic fashion, results in the formation of phenyl free radical. And once you get this phenyl free radical, as you can see, the carbon is having 1 unpaired electron here. Okay, so once you get phenyl free radical, exactly the same way, we got one more reaction taking place here, and the reaction is alkyl halide and sodium, again exactly the same like the first reaction here. So it generates a carbon free radical, any alkylic can be. Then these two free radicals combines to form alkyl arene. Right, that's a simple reaction. So the intermediate here involved in this one is like getting a free radical formation, and these two free radicals combining to form a neutral molecule, like can take it as alkyl arene. Right, that's the Wurtz-Fittig reaction. The next reaction we got is Fittig reaction, and in the case of Fittig reaction, so we got 2 moles of aryl halide on reaction sodium in the presence of dry ether, results in formation of a compound diphenyl. And if you take mechanism for this reaction, again the same, so you get generation of, in the previous you got like 1 phenyl free radical and 1 alkyl free radical, but in this one you get generation of like 2 moles of phenyl free radical from this halorine, and those phenyl free radicals will join to form the compound diphenyl or biphenyl. Alright, the main difference now between 3 reactions, Wurtz reaction, Wurtz-Fittig and Fittig reaction, will be, in Wurtz reaction we'll get like 2 moles of alkyl halide. In Wurtz-Fittig reaction we take 1 mole of alkyl halide and 1 mole of aryl halide, and in Fittig reaction we take 2 moles of aryl halide, all the same reaction with sodium metal in dry ether to form the respective compounds. Alright, that's 3 similar reactions. The next reaction, okay, we got from here onwards the reactions. Okay, you got this reaction, haloalkenes and haloarenes, and these two reactions, Finkelstein and Swart's reactions, are the preparations for haloalkenes. Let's take first reaction now, the Finkelstein reaction. Right, Finkelstein reaction is conversion of alkyl chloride or bromide into alkyl iodide. Now in this conversion, can starting with the chloride or bromide with alkyl iodides. So we're actually starting with alkyl halide only and preparing alkyl iodide in particular. So we can take this one in place of like chlorine and bromine. Now we are adding iodine So it means we can take this reaction as like it's exchanging the halogens. So this reaction is halogen exchange reaction. Right, so when alkyl chloride or bromide is treatment to sodium iodide in organic, like even solvent is not cannot mentioned here, plays a very important role. Triacetone also. In the presence of triacetone results in formation of alkyl iodide, and along with that get byproduct. Right, I said it plays a role in triacetone, and the role of that we can take it as you can see in triacetone, sodium halide will precipitate out easily, and once it is precipitated out or removed from the aqueous solution form, the other solution form, so you can apply the Lee-Chatterley's principle here, as if you remove this NaS or if it is precipitated, the reaction will shift in the forward direction according to Lee-Chatterley's principle, and the forward reaction is nothing but the formation of getting more and more alkyl iodide. So we'll get better yield of alkyl iodide if you take the reaction in triacetone. So that's the reason why the solvent also plays a very important role here. Right, that's a Finkelstein reaction. Chloride or bromide in the place of Cl or Br, are getting I, preparation of alkyl iodide. The next reaction is similar, Swart's reaction, and in this reaction we take the conversion of alkyl chloride or bromide, again same, into alkyl chloride. Right, I take one example here, methyl bromide, and the reagent here in the previous you got reagent is like sodium iodide, and in this method we got reagent is any metallic fluoride can be used. For the examples given here, metallic fluoride can be AgF, HgDF2, COF2 or SbF3. Right, on heating with these metallic fluorides, we can convert alkyl chloride or bromide into alkyl fluoride. Right, this is the conversion of methyl bromide into methyl fluoride by using silver fluoride here. I take one here, or you can take any metallic fluoride, just we need to heat it. Right, that's a reaction called Swart's reaction, method of conversion of alkyl chloride or bromide into fluoride. Right, the next one we got is Grignard reagent. As you got this one also in halogens only. This reaction of alkyl, let me take first generally before going for this Grignard reagent. You already know the meaning of organometallic compounds. And in the case of organometallic compounds is nothing but or will get generation of formation of these compounds will be when alkyl halide reacts with metals, and those compounds what you get upon reaction of alkyl, or can take it can be chloride, bromide or iodide with certain metals, and those compounds obtained will be having a bond between carbon and metal, and those compounds we call it as organometallic compounds. And if the metal taken as magnesium, then the obtained compound is called the Grignard reagent. Right, you can take a formula for Grignard reagent as like as alkyl magnesium halide. You can take formula like RMgX. Now how you get this Grignard reagent? So let me take first one reaction here. I take an alkyl halide like ether bromide on reaction with magnesium in presence of dry ether results in formation of, so we'll get alkyl magnesium bromide here, particularly ethyl magnesium bromide, and it is said to be Grignard reagent because we got magnesium, or can take alkyl magnesium halides. It is right. That's the generation of Grignard reagent. Now what for we can use this reagent? As you can see in organic synthesis, this is a very important reagent which can be used in many reactions. We're not having all the reactions given for the class 11th and 12th. So what you do is just discuss those reactions which are having actually. The first reaction given is the reaction of this Grignard reagent. It can be taken with any compound which is acidic in nature. And the second one is we got the reaction Grignard reagent with any carbonyl compounds. It can be aldehyde or ketone, which you'll get in the topic alcohols, phenols and ethers. Is actually preparation of alcohols by using carbonyl compounds and Grignard reagents. Right, so before going for the reaction one reaction here, let me take if you take structure of this RMGX, and if you write the charge separation and the bonding actually in this between carbon magnesium halogen, you can say magnesium halogen, it has to be the ionic bond between these two. And if you take RMG, or can take carbon and magnesium, will be having covalent bond. And if we take this covalent bond, the bonding electrons are more towards always carbon, as well as that's more like negative compared to magnesium. So that's the reason why this bond between carbon and magnesium is highly polar bond. And if I say this highly polar bond can be broken very easily to form, it generates the species in which carbon is having a negative charge. So this is a good source for getting the nucleophiles, right? And the nucleophiles the carbon ion. Right, so let me take one reaction for this now. Grignard reagents are highly reactive and react with any source of proton to give hydrocarbon. Always a function of hydrocarbon here. Okay, can be proton donor or any compound actually which donates the proton can be taken as water or alcohol or amines. Okay, so one reaction is given here, RMGs plus H2O. As you know, this H2 will donate a proton H plus, or can take this R minus carbon ion, will just abstract one proton and convert it into RH, and along with that we'll get a byproduct here NGOH. Right, this is the same, we get in all cases we get same RH if the compound or treatment with any compound which is a source of proton. Right, this is one reaction. And I said we got here in preparation of alcohols also. I added that reaction in the next video, which will be covering again the same number of reactions, like 12 or 15 named reactions. Right, so the next we got is, and today's last reaction, Sandmeyer's reaction. Right, so Sandmeyer's reaction is the preparation of haloarenes from diazonium salt. Right, now when you convert diazonium salt into haloarene, and we take in Sandmeyer reaction the reagent as like Q plus halide. It can be Q plus chloride or Q plus bromide. But as you can see, diazonium salts, so first we need to prepare these, right? And the preparation of diazonium salts can be taken by a reaction called diazotization. And in diazotization we take aromatic amine, like we take aniline. Upon reaction with diazotization we got the reagent for that, right? You can take HNO to nitrous acid, or getting mixture of like NaNO2 and HX. It can be any acid, okay, any halogen, right? Preferably HCl we take in the temperature range of 0 to 5 degrees Celsius. Results in formation of benzene diazonium halide. Right, so the first step is you need to get diazonium salt, and once you get diazonium salt we can easily replace this diazo group by the halogen by treatment with Q plus halide. Right, so once you get diazonium salt, treatment with Q plus salt, chloride or bromide results in formation of aryl halide with elimination of N2 molecule. Right, this reaction is called Sandmeyer's reaction, and having like first we need to get diazonium salt by using diazotization reaction, and the second one treatment with Q plus salt to form haloarene. Right, so this is about Sandmeyer reaction, and let me take the mechanism for this reaction, how it takes place. So for the mechanism I have taken a substituted one, diazonium ion here, or it can be any alkyl. So in the first step, as you can see, the reagent used is Q plus salt, and Q plus salt or Cu plus 1 will lose one electron here first, and if it loses one electron, and this bond is also going to be broken in the first step only, N2 will be eliminated, nitrogen molecule, and as this is giving one electron, we'll get formation of a species in which carbon is having one alkyl electron. I can take it as like a free radical. So we get like a substituted phenyl free radical in this one, and once you get this free radical, the next step will be the reaction with the counter ion for the Cu plus. We got a halide X minus, then this halide will attack on this, and simultaneously, as again this carbon is having only one electron there should be elimination of one electron so that it forms a bond with this carbon. So we get new bond formed here between carbon and halogen with the elimination of, I can take like removal of one electron, and this electron is abstracted by the Cu2 plus to convert into Cu plus 1. Right, so you got again the similar one, right? What used in the first step, we're going to get it back in the last step, Cu plus 1, and we're converting, or can take like replacing N2 plus group by X, so that we get formation of haloarenes. Right, this is the last reaction in today's video. So we are taking totally 12 named reactions in this video. So what I'm going to do, this is actually going to be part 1 out of 3 parts. So in the next video I'm going to add like 12 to 15 named reactions. So it'll be having third part also, which covers all the reactions, or can take remaining reactions. Okay, right, this is about the first part out of 3 parts. So if you like this video, please like, share and comment and subscribe to my channel. Thank you.